The first step in manufacturing steel pipes is edge milling. This process is crucial for achieving precise dimensions and a uniform edge profile. The raw steel coil or plate is fed into the edge milling machine, which employs high-speed rotating cutters to trim the edges. After edge milling, the steel strip undergoes the 3-roll machine process. This step involves passing the trim strip through a set of 3 rollers that gradually bend it into a circular shape. The rollers exert immense pressure on the steel, causing it to curve while maintaining a consistent diameter. In some cases, particularly when manufacturing large diameter or thick-walled pipes, a post-bending step may be necessary. Post-bending helps achieve the desired curvature and circularity of the pipe. Once the steel strip has been bent into the preliminary pipe shape, the next step is tack welding. Tack welding involves creating temporary welds at specific intervals along the length of the pipe. These welds hold the pipe's shape and prevent it from distorting during subsequent manufacturing processes. After tack welding, the partially formed pipe proceeds to the pipe processing stage. This step involves a series of operations to refine the pipe's shape, size, and surface finish. Various machines and tools may be employed during this stage, including sizing mills, rotary expanders, and straightening machines. Sizing mills ensure that the pipe attains its final diameter, while rotary expanders improve its roundness and straightness. Internal welding is a pivotal stage in the manufacturing of steel pipes, focusing on creating robust and reliable seam connections along the pipe's length. During this process, the edges of the steel strip or plate are brought together and fused through welding techniques such as electric resistance welding, ERW, submerged arc welding, SAW, or high-frequency induction welding, HFIW. The goal is to create a secure continuous weld that maintains the pipe's structural integrity and prevents leaks. Quality control is paramount in the manufacturing of steel pipes. Visual inspection plays a crucial role in identifying and rectifying any defects or imperfections in the pipes. Trained inspectors carefully examine the surface of the pipes for issues such as cracks, pitting, or irregularities. They also check for proper weld penetration and alignment. Any detected defects are marked for repair or rejection. Visual inspection ensures that only high-quality pipes progress to the next stages of manufacturing. Before the final welding and heat treatment processes, the pipes must undergo pre-washing. Pre-washing is essential to remove any contaminants, residues, or oils from the pipe's surface. These impurities can interfere with the welding process and affect the quality of the final product. Pre-washing machines use a combination of high-pressure water jets and chemical solutions to thoroughly clean the pipes. This step prepares the surface of the pipes for the subsequent welding and heat treatment processes, ensuring proper bonding and structural integrity. The last critical step in the manufacturing of steel pipes is the use of an X-ray real-time machine for non-destructive testing, NDT. This machine employs X-ray technology to inspect the internal welds of the pipes in real time. It allows inspectors to identify any weld defects, such as porosity, lack of fusion, or cracks, without damaging the pipes. The real-time nature of this inspection ensures that any issues are detected immediately, allowing for prompt corrective action. Pipes that pass the X-ray inspection are considered fit for use, meeting the highest quality and safety standards.
The production of ADP water pipes begins with the preparation of raw materials. High-quality ADP resin, additives, and colorants are selected based on the required specifications and standards. The raw materials are carefully measured and mixed to achieve the desired material composition. Once the raw materials are prepared, they are fed into an extrusion machine. The extruder melts the ADP resin and feeds it into a heated barrel under controlled temperature and pressure. The molten ADP is then forced through a die, which gives the pipe its desired shape and size. Quality control is a critical aspect of ADP water pipe manufacturing. Various tests are conducted to ensure that the pipes meet the required standards and specifications. These tests include measuring the diameter, wall thickness, and length of the pipes, as well as conducting pressure tests to check their structural integrity. Once the DN800 ADP water pipes are manufactured, they can be installed using the relining technique. Relining involves inserting a new pipe inside an existing damaged or deteriorated pipe, providing a cost-effective and non-disruptive solution for pipe rehabilitation. The process begins by preparing the ADP pipes for installation. The pipes are selected based on the required specifications and cut to the appropriate length. The pipes are then placed in the cell of the welding machine, which securely holds them in place during the subsequent steps. The processed ends of the pipes are thoroughly cleaned to remove any dirt, debris, or contaminants. Clean and smooth pipe ends are essential for achieving a proper and secure connection. Knives or cutting tools specifically designed for pipe processing are installed. The processing of the pipe ends involves trimming and smoothing the edges to ensure they are even and free from any irregularities. This step helps in achieving a precise and tight fit between the pipes. A Teflon heater is placed between the processed ends of the pipes. The Teflon heater acts as a heating element to soften the ADP material. The pipe ends are heated to a specific temperature, causing the material to melt and become pliable. Once the desired temperature is reached, the pipe ends are pressed together firmly, creating a strong and secure connection. This process is known as butt fusion welding. Passing through existing pipeline. After the ADP pipes are successfully connected, the connected pipes are carefully passed through the existing steel pipeline. This step requires precision and caution to avoid any damage to the pipes or the existing pipeline. The relining process utilizing ADP water pipes provides several advantages, including improved flow capacity, increased longevity, and resistance to corrosion. By following these steps in the manufacturing process of ugradna or relining ADP vodovodny pipes, efficient and reliable rehabilitation of water pipelines can be achieved, contributing to the overall efficiency and sustainability of water distribution systems. The concrete mixing process can be performed using various methods, including manual mixing or mechanical mixing. In mechanical mixing, uncrete mixer is commonly used. The mixer has rotating blades or paddles that thoroughly mix the ingredients, ensuring uniform distribution and achieving a consistent mixture. Once the concrete mixture is prepared, the next step is to prepare the molds for pipe formation. The inner and outer molds, which determine the shape and dimensions of the pipes, are assembled and adjusted according to the desired pipe specifications. These molds are typically made of steel or other durable materials. To facilitate the easy removal of the formed pipes after curing, release agents may be applied to the inner surfaces of the molds. These agents create a thin film that prevents the concrete from sticking to the molds, allowing for smooth demolding and minimizing the risk of damage to the pipes. With the molds prepared, the concrete mixture is fed into the mold assembly through the concrete supply system. The supply system can include a hopper, conveyor belt, or other feeding mechanisms that transport the concrete to the mold. During the concrete placement process, the vibration mechanism of the machine is activated. The vibration helps to compact the concrete and eliminate voids or air pockets within the mixture. The core vibration method is particularly effective in ensuring proper compaction and achieving uniform density throughout the pipe. This compaction process improves the strength and durability of the pipes, reducing the risk of cracking or structural failure. After the concrete is placed and compacted in the molds, the pipes are left to cure. Curing is the process of providing favorable conditions for the concrete to hydrate and gain strength. The curing time may vary depending on factors such as the type of cement used and the desired strength. Development. During this period, it is important to maintain appropriate temperature and moisture conditions to promote proper hydration and curing. Once the concrete has achieved the required strength, the molds are opened, and the pipes are carefully demolded. This is done with caution to avoid any damage to the freshly formed pipes. After demolding, the pipes may undergo additional finishing processes to enhance their appearance and durability. These processes can include surface smoothing or coating, which improve the aesthetics and protect the pipes from external elements. The finished pipes are then handled and stored for further curing, allowing them to continue gaining strength and durability. Alternatively, the pipes can be transported to the installation site for immediate use in various infrastructure projects such as drainage systems, sewer lines, or culverts. The process begins with the preparation of the reinforcing cage. Pre-tension PC prestressed concrete bars are cut into specified lengths and assembled to form the reinforcing cage for the pile. The bars are securely welded together to create a robust and stable structure that will provide reinforcement to the concrete. Next, the concrete mixture is prepared. The concrete is typically mixed with suitable admixtures to enhance its workability and strength. The prepared concrete is then poured into a spinning mold, which is already equipped with the reinforcing cage. During the pouring process, pre-tensioning strands or bars are inserted through the cage to add pre-stressing force to the pile, which improves its load-bearing capacity. Once the concrete is poured and the pre-tensioning is complete, the spinning mold is rapidly rotated using a centrifugal procedure. This spinning action helps to evenly distribute the concrete and remove any air voids or imperfections. This centrifugal force ensures uniform density and strength throughout the pile. After spinning, the concrete undergoes an initial curing phase to allow it to gain sufficient strength. After the initial curing, the piles are transferred to a steam curing chamber. Steam curing is a controlled process that involves exposing the piles to high-temperature steam. This accelerated curing method helps in achieving early strength development and enhances the overall durability of the piles. The steam curing process typically takes a few hours to a few days, depending on the specific requirements. Once the steam curing is complete, the piles are demolded carefully. Demolding involves removing the spinning mold, leaving behind the hardened concrete pile. The demolded piles are then subjected to water curing, which involves keeping the piles moist by regularly spraying or immersing them in water. Water curing allows for the hydration process to continue, enhancing the strength and durability of the piles over time. By following these steps, the spun pile BGA manufacturing process ensures the production of high-quality concrete piles with excellent load-bearing capacity and longevity. Each step is carefully executed to achieve consistent and reliable results, making spun pile BGA piles a preferred choice for various construction projects. The production process begins with the use of directly reduced iron ore as the raw material. This iron ore is charged into a 30 metric ton mega furnace using giant electromagnets for melting. Once the charging is completed and the desired temperature of 1650 degrees Celsius is achieved, the melting takes place in a cordless induction furnace. This furnace consists of a refractory container surrounded by a helical coil connected to an alternate current source. This setup facilitates the melting of the iron ore. After the molten metal has been extracted from the crucible onto the casting ladle, it is purged with nitrogen to ensure a homogeneous chemistry and uniform temperature throughout the ladle. After the molten metal has been extracted from the crucible onto the casting ladle, it is purged with nitrogen to ensure a homogeneous chemistry and uniform temperature throughout the ladle. Once the molten metal is extruded from the mold tube, it enters a containment section with primary and secondary mist-type cooling chambers. This process ensures the integrity of the cast shape and maintains a balanced quality. The solidifying bullet is then cooled to the desired rolling temperature and length. At this stage, it is cut by online bullet shears and sprayed with water through special nozzles for solidification and uniform cooling. These hot billets are transferred to the rolling mill without wasting time or energy. The gradual size reduction process begins on a straight line continuous rolling mill. The hot billets undergo size reduction in the roughing mill, intermediate mill, and finishing mill. Rolling continues until the desired finer grain structure of the steel bar is obtained. The rolling and guiding technology employed at FI is sourced from Daniele Mortardschammer, Italy. The loop scanner in the flow of the bar ensures a tensionless rolling process, contributing to the perfectly round shape of the bar. After the final finishing stand imparts its impression on the rebar, they enter the quenching system, which establishes their tensile strength. The bars can be tempered within a desired range, from Fe 415 to Fe 600, according to the specific requirements and demands of customers. Subsequently, the bars are cut into 60-meter sizes by online dividing shears. In the cooling section of the steel bar manufacturing process at FI, atmospheric tempering is conducted at the cooling bed. This step is crucial in enhancing the properties of the steel bar. During atmospheric tempering, the hot core of the bar releases heat to the surface. This controlled cooling process creates a temperature gradient within the bar. As a result, the bar develops a soft core that offers flexibility, while the surface of the bar becomes hardened, providing strength and improved grip. The formation of a soft core and hardened surface in the steel bar is essential for its performance in various applications. The flexibility of the core allows the bar to absorb and withstand stresses, making it resistant to deformation and cracking. The hardened surface, on the other hand, provides increased strength, making the bar capable of withstanding heavy loads and structural demands. Additionally, the hardened surface also enhances the grip of the bar, ensuring better adherence and bonding with concrete or other construction materials. Moreover, the atmospheric tempering process contributes to the corrosion resistance of the rebar. By carefully controlling the cooling conditions, the steel bar's microstructure is optimized, reducing the risk of corrosion and extending its service life in harsh environments. At Prakash Ferris Industries Private Limited FI, the bundles of rebars are meticulously prepared to meet the specific requirements of customers. These rebars are available in variable sizes and can be produced as both straight and bend rebars, all done without any manual effort. Once the steel bars have undergone the necessary cooling process, they are carefully packed into bundles. The bundles are then stored inside spacious indoor warehouses, covering an area of 80,000 square feet. The storage of the rebars is organized based on their sizes, grades, and lot numbers. This meticulous organization allows for easy retrieval and efficient inventory management. By categorizing the rebars according to these parameters, FI ensures that the specific needs of each customer can be met promptly and accurately. To streamline the bundling process, FI employs advanced technology from Sundbersta, Sweden. Online master bundling and bend bundle making PLC-controlled automatic machines are utilized. These machines are equipped with programmable logic controllers PLCs that automate the bundling process with precision and reliability. The PLCs enable the machines to perform tasks such as measuring and cutting the rebars to the required lengths, arranging them in desired configurations, and securely bundling them together. The online master bundling machines efficiently handle the straight rebars, while the bend bundle making machines specialize in creating bundles of bend rebars. The use of these automated machines ensures consistent and accurate bundling, minimizing human error and maximizing productivity. By utilizing the state-of-the-art technology and automation provided by Sundbersta, FI ensures that the rebars are bundled efficiently, meeting the specific needs of customers. Quality control is a top priority at FI. Stringent tests are conducted after the rolling process to reaffirm the quality of the end product. To sustain the high standard of rebars, 100%, machining and embossing of the rolls are performed at the state-of-the-art in-house.
Weckenman specializes in the design and manufacturing of equipment and systems for precast concrete plants. With decades of experience, the company has gained a deep understanding of the unique requirements and challenges of the precast concrete industry. Weckenman's circulation plant is the heart of the operation. It's a versatile system that enables the production of both solid and sandwich elements. These elements form the core structure of many construction projects. To create the desired shapes and dimensions for precast elements, magnet shuttering profiles are used. Weckermann's profiles securely hold the concrete in place during casting and curing, ensuring accurate results. Freshly mixed concrete is transported from the batching plant to the casting beds using a rollover bucket conveyor. This system allows for precise pouring of concrete into the molds, minimizing waste and ensuring consistency. The concrete spreader's role is to evenly distribute the poured concrete within the molds. It plays a crucial role in achieving uniform thickness and consistency across the precast elements. After the concrete is distributed within the molds, a vibro screed is used to vibrate and level the surface. This process removes air voids, ensures a smooth finish, and enhances the structural integrity of the elements. Proper curing is essential to develop the required strength and durability of precast elements. Curing chambers provide a controlled environment with the right temperature and humidity conditions for the curing process. For precast elements requiring a superior surface finish, a helicopter troweling machine is employed. This machine provides a high-quality, smooth surface finish to the elements, making them visually appealing. Special architectural pieces or unique elements may require customized molds and casting methods. Tilting tables are used to manufacture these distinctive elements efficiently and precisely. High-frequency vibrators are essential for compacting the concrete mixture thoroughly. Proper compaction ensures that the concrete reaches its intended strength and durability. Weckermann provides customized solutions tailored to the specific needs of precast concrete manufacturers. This includes circulation plants for solid and sandwich elements, battery molds, magnet shuttering profiles, and more. These solutions are designed to optimize production processes and improve product quality. Battery molds are versatile and efficient, allowing for the production of various precast elements, including stairs. These molds simplify the manufacturing process for complex and specialized components. Weckermann is at the forefront of technological advancements in precast concrete manufacturing. Their equipment incorporates cutting-edge automation, robotics, and digital control systems to streamline production, reduce labor costs, and enhance precision. Battery molds are also used for producing solid walls and floor slabs. They offer a standardized and efficient approach to manufacturing these essential building components. Weckermann's equipment is designed with a strong focus on quality assurance. Their solutions help ensure that precast concrete elements meet stringent quality standards, providing structural integrity and durability in construction projects. Battery molds are also used for producing solid walls and floor slabs. They offer a standardized and efficient approach to manufacturing these essential building components. Weckermann is committed to sustainability and environmentally responsible practices. Their technology often contributes to reducing material waste and energy consumption in precast concrete production. One of Weckermann's notable offerings is its circulation plant, which is instrumental in producing solid and sandwich elements used in construction. These plants are designed to optimize the manufacturing process, ensuring precision, consistency, and efficiency. They also integrate state-of-the-art automation and digital control systems, reducing labor costs and minimizing material waste. Weckermann is known for its commitment to sustainability. Many of its solutions contribute to reducing energy consumption and waste in precast concrete production. Aligning with environmentally responsible practices, This commitment to eco-friendliness is especially critical in today's construction industry, where sustainability is a top priority. Precast concrete foundation piles are crucial for many construction projects. Specialized molds are used to create these load-bearing elements efficiently. In some cases, precast concrete elements are designed with integrated ceramic tiles for architectural and aesthetic purposes. This adds a decorative aspect to the elements, enhancing their visual appeal and versatility. Their technology plays a crucial role in meeting the growing demand for efficient and sustainable construction solutions worldwide.
The process begins at the pallet cleaning station. Pallets or molds, which serve as the foundation for the concrete elements, are meticulously cleaned and inspected. Precision is paramount in precast concrete production. At the plotting station, skilled workers meticulously plan and lay out the design for each concrete element. The next step takes place at the shuttering station. Shuttering, also known as formwork, is the framework into which the concrete will be poured. Skilled craftsmen assemble and position the formwork with utmost accuracy, ensuring that it corresponds precisely to the design specifications. To prevent the concrete from adhering to the formwork, a release agent is applied. Structural integrity is achieved through steel reinforcement. At this station, steel cages or reinforcement bars are fabricated to the required specifications. These cages are strategically positioned within the formwork, adding strength to the concrete element and enabling it to withstand the intended loads. The batching plant serves as the central nerve of a precast concrete facility, where meticulous precision is paramount. Here, the raw materials, including cement, aggregates, such as sand and gravel, water, and occasionally admixtures, are meticulously measured and blended to create the precise concrete mixture required for each specific project. This process demands unwavering accuracy, as even minor variations can profoundly affect the concrete's strength and durability. Achieving the perfect mix ensures that the resulting precast concrete components meet stringent quality standards, offering structural integrity and longevity for the diverse range of construction applications they are intended for. Write more detail about once the concrete is poured into the formwork, the curing process begins. The curing chamber provides controlled environmental conditions, such as temperature and humidity, necessary for the concrete to gain strength gradually. Proper curing is essential for the concrete to achieve its intended performance characteristics. In about 70 words. After the concrete has reached sufficient strength, it is time for demolding. At the stripping station, the formwork is carefully removed from the concrete element. This process requires precision to prevent damage to the newly cast component. Once demolded, the concrete element is inspected for quality and conformity to project specifications.